Let's take a quick look at some of the input needed from climate change science or Earth system science to advise on policies for mitigation and adaptation and the planning that go with it. So here we are starting with global climate models, which are, let's say, used in IPCC AR4. AR5 already had many Earth system models, which basically included carbon cycle for sure, ecosystems, and ocean biogeochemistry. So biophysical and biogeochemical feedbacks were done. Human beings are not entirely part of the system, and the coupling with the social module is not there yet. And you also have simple climate models and regional climate models. So here it's time to emphasize again that adaptation by definition is very local. So you need regional and local information, not only to help adaptation policy and planning, but also to avoid maladaptation. So we will see examples where you could be doing the wrong thing and end up with unintended consequences that are actually not helpful for climate adaptation to the impacts you will be facing in that region. So there are global impacts, so they are 30 to 100 years and beyond in terms of sea level, because CO2 residence time is long, and even if you manage to reduce emissions or even take it to zero, we see that the CO2 and the warming are going to continue for several centuries. In fact, unless the CO2 capture and sequestration is going to bring it down dramatically. We will see those numbers a little bit later on, but those are going to affect the local impacts at months to seasons and multiple decades in terms of, let's say, how climate change is going to affect cyclones in your region, the monsoons, how urbanization and land use change are going to mix with these biophysical climate changes and create issues that require adaptation policy and planning. And the climate models can feed those, but you can also often combine with simple climate models for some issues that we will look at as examples. And there are initial conditions provided by these global climate models to regional climate models. So basically regional climate models are done to increase resolution and sometimes improve the local land use change representation, better represent the mountains, better represent the land-atmosphere interactions or the ocean-atmosphere-land interactions, in this case of the UK, and so on. So when you have a regional model, you need to prescribe the winds, temperatures, humidities, and so on at the boundaries. In the ocean, you will need tides, sea level, currents, temperatures, etc. So those are often provided by the global climate models, but if it's being done for the past, there are also other sources like from data or reanalysis that we talked about, the products that mix models and data to produce dynamically interpolated past climate information can also be used for these things. So that is then has to be considered in the context of anthropogenic forcings and socioeconomic impacts. They are not obviously linearly related. There are feedbacks which make it quite nonlinear. So in terms of linear chains, we would think about greenhouse gas emissions, increasing greenhouse gas concentrations, typically in the atmosphere, but also in the ocean in terms of ocean acidification, global climate change, as we discussed already, local climate change to make it region-specific changes, let's say in extreme events or sea level rise, biophysical impacts on vegetation, fisheries, crop yields, vulnerability of agriculture, forests, and so on, and translate that into socioeconomic impacts. But in reality, a wider view is needed where you have the same links, but you need feedbacks from biophysical impacts to greenhouse gas emissions and concentrations and climate change via changes in albedo, humidity, local impacts on local climate and local climate change, and you have to also consider non-greenhouse gas drivers of global and local climate change. We will see these in more detail, but just keep that in mind as you go forward. There are non-climate effects of greenhouse gases in terms of biophysical impacts. So that could be crop yields, health outcomes. So these are not climate impacts, but for example, demand for air conditioning would go up, various other loss of employment and so on can also happen. And changes in vulnerability are going to be associated with socioeconomic impacts, which are going to obviously have interactions between socio-economic impacts, mass migration, climate migration, for example, and so on. So obviously the system is very much nonlinear. In that context, you need some metric of a risk faced by, let's say, communities or regions, and risk is defined as hazard times vulnerability. Hazard here could be frequency of floods, frequency of droughts, sea level inundations, and so on. And this was used in the assessment report 4 that came out in 2007. But in the 5th assessment report, they modified this slightly to add exposure to this product. So that's the chances of you being exposed. So even if you are in a region which, let's say, has increased heat waves, if you are well off socioeconomically and you are living in a nice air-conditioned apartment, or it could be air pollution increase and you are able to protect yourself with various mechanisms, having air filters, air conditioners, etc., then your exposure is going to be different than somebody who's living in a slum or doesn't have the socioeconomic wherewithal to protect against, let's say, air pollution or heat waves. So those are important. In that sense, adaptation tries to reduce vulnerability, hence risk, whereas mitigation is aimed at reducing the hazard itself, right? So we're trying to reduce our impact on climate change, which means we're trying to reduce the hazard introduced by anthropogenic forcing of climate change. So here, this is from this paper here, looking about hazard as dangerous phenomenon. Vulnerability could be physical, could be social, could be economic, environmental, and they are coping and adaptive capacities. So if you are poor, you're not able to easily move away from the coast, or if you're a fisherman, you're not able to find another livelihood. For example, if you're a farmer, you're not able to move to another job, and so on. Exposure is a function of structures, population and population density, agriculture, business, and assets you own, etc. Okay, the intersection of these, as we saw, gives us risks, and risk is defined with respect to a particular recipient. That's what we mean by exposure. It's not the same for everybody. That's where socioeconomics becomes very important. This recipient, such as a species, a business, a country, or a person. Okay, hazard is an external factor. And nature and magnitude of climate change will often determine the hazard. It could be hydroclimatic, for example. While vulnerability is a property of the recipient, for example, different recipients may have different levels of vulnerability to the same hazard, as I already mentioned, in terms of air quality and heat waves, and may be exposed to different levels of risk. For example, river flooding, the hazard is the extreme rainfall and the resulting increase in river levels, while vulnerability is a function of the location of the buildings, existence of flood defenses, preparedness of the residents for coping with flooding, and so on. This also includes early warning systems that some nations have built, weather forecasts used to warn people about coming floods, and closing down schools and transportations, infrastructure, etc. Adaptation can be considered to be largely about reducing vulnerability, while mitigation is about reducing hazard, which makes more sense in this context here. So we will come back and look at the details of the Earth system for the science of mitigation and adaptation.